All right, guys. Hey, welcome back to another fabulous lesson in kinetics. So here we are back in kinetics still. This is big idea 4. All right, so I want to talk a little bit about what's called the collision theory. So the idea with the collision theory, and I've referred to this a little bit, is that all chemical reactions occur because, and let's get a couple different colors right here, because you've got particles that are hitting each other, and when they collide, the collision theory, when they collide, at some point they have sufficient energy, and when they have sufficient energy, they form, so let's see, well this will be, they form what's called an activated complex. So the activated complex is this high energy state, where it's the highest energy state that it has right here. And once they form the activated complex, they have what's called sufficient energy. And that sufficient energy means that they have reached activation energy, or what we call EA. So they activated, and then this particular activated complex will then go and react, right? So that means the reaction will occur. So in any chemical reaction, there's a combination of what we would call ineffective collisions that just bang into each other, and for one reason or another, either because they hit in the wrong side or not with enough force, they don't form an activated complex, and so then they don't reach activation energy and so forth, and then they do not lead to a chemical reaction. So in every single overall chemical reaction, there's some collisions that are insufficient or ineffective and some that are sufficient. And so analyzing these things is important. And so a couple of the things that we've talked about is that when you increase the concentration, say I start throwing more of these things in here, right? So if there's more of these in here, well, these things are going to hit each other more often. So a couple of things. So increasing concentration of the reactants will cause the reaction rate to increase just because there's more of them in there. So whatever you do to smash these together more, it's going to increase the rate of the reaction, right? If I changed the volume, if I made this volume smaller and kept the same amounts in there, it's going to increase the reaction rate because now they have less room to move around, so they're going to hit each other more often. Another thing that increases reaction rate is increasing temperature. Because what's going to happen is that the temperature is actually going to cause these to move more quickly. If they move more quickly, they're going to smash each other more often. They smash each other more often, they're going to create activated complexes with more energy more often. And so sometimes in chemistry we look at something like this. This is called a Boltzmann distribution diagram. And what you can see right here is this is a lower temperature, and so this is the average kinetic energy at a lower temperature. And so this is the probability of a particle interacting with that kinetic energy. So here's my kinetic energy, but this is the kinetic energy increasing along the x-axis here. So you see, in order to reach an activation energy, you have to get to this point. So most of my particles at my low temperature are hitting around here, and a small portion of them will hit around here. Now, if I increase the temperature, you see what that does? That changes the fraction, doubles it in this case, doubles the fraction or the amount of particles that are hitting each other with enough force to reach activation energy. So the temperature will increase the reaction rate. So temperature changes the reaction rate as well. And so we have an equation that helps us to figure out what the rate constant will be, or to calculate the rate constant when temperatures increase. And so the relationship between temperature and the rate constant is given by what's called the Arrhenius Equation. Now this, like our other equations that we use the calculus in order to fix, like in the previous videos, this is the same thing. This is also a linear equation. So this is like an mx, let's see, wait, sorry. This would be a y equals mx plus b. So if I was to say, graph this out right here, if I was to graph this out right here, I would have my natural log of my rate constant, because the y is going to be my rate constant. So the natural log of my rate constant, and my x is going to be 1 over the temperature in Kelvin. All right, and then so, let's say that I graph that out like that. And so then my slope, right, is going to equal my negative activation energy divided by my gas constant, which is 8.31 joules per Kelvin moles. All right, so that's my R right there. I'm just writing that in there. So this is going to be the slope. So it's my y equals mx plus b. So some other parts here. What's the natural log of a? So a is a constant in this case that takes into account the collision frequency and orientation. So that's probably something that you would be given in one of these situations. But just to look at this, if you're able to kind of understand this, what this is telling you is that that the constant here, K, will actually increase as the temperature right here increases. And so that's really all that you're supposed to get from this. And I don't know if you'll ever be given anything where you have to use the Arrhenius equation to solve it, but you might be asked what it's telling you. And so what it's telling you is essentially that the rate increases when the temperature increases. And you might have to do something like this to prove it. But remember, this is a y equals mx plus b. And if you graph this out, if you just made a graph like this, you could just say as temperature increases, the rate constant will increase. All right, so in the next video, we're going to look at reaction mechanisms a little bit. And this is just kind of like an FYI, kind of get this content knowledge in your mind. And we'll do some practice problems.